Hi guys, Ms. Peterson here, and welcome to AP Physics 2, Lecture 7-4, all about spacetime and relativity. If you've been here, this is it. This is the last lecture in our AP Physics 2 curriculum, which is cool because it's also one of the shortest. Okay, in this lecture, we're going to be talking about spacetime and relativity, and a little bit back to the de Broglie wavelength and show you one more series on that. Okay. But first, we need to understand spacetime. And this is not an easy thing to understand, okay? Not easy in the way that I don't have the visualizations I would need to be able to communicate this well. So I want you to pause this video right now and go watch the fundamentals of spacetime from TED Ed. All three of these videos are excellent visuals to show you how speed dilation and time contraction functions based on our understanding of space-time. Okay, so go watch those videos, then summarize them in your own words here. Okay, in my words, okay, the speed of light is constant. And space-time shifts to make this true for all observers. Okay, and that is kind of the underlying principle too of relativity. Okay, when we talk about relativity, this is this idea that motion can only be described relative to an observer, okay? We need to have some reference frame for it. And then the fundamentals of relativity are that the laws of physics should be the same no matter whose reference frame you are looking through, okay? Basically, if the speed is distance over time, that should be the same no matter who's looking for it. And that speed is the same. Okay, so I'll show you a little bit of how this kind of works. One of the ways that we can understand this is through something called muons. So muons are subatomic particles that travel near the speed of light, and it decays. So basically, if we had an observer on the ground, they would look and see it traveling at some speed v and see it go this distance, okay? And that will take some amount of time, t. Now, for the muon, okay, it decays after a time t. And according to its reference frame, okay, it doesn't have time to go that 2.01 kilometers, okay? It only has time to go 6.27 kilometers before it decays. So that's the distance from the muon's perspective, okay? It has that same path. It's traveling at the same speed, the speed of light, okay? But the motion of everything else relative to it seems to be smaller, okay? This might be even easier to visualize if you're thinking about an astronaut on the space shuttle, okay? So we have an astronaut on this rocket, and the astronaut shines a light that hits a mirror and travels back to the receiver, moving some distance d, there and back, okay? But if this is moving, according to an observer on Earth, that light would have had to go this distance. Not just that distance, a much greater distance. And since this observer on Earth has to agree with the speed of light for this astronaut, okay, their times are different, okay? This one sees a longer time between those two events, the light being shined and the light being received. Where for the astronaut, the speed is the same, and speed is distance over time. So if the speed is the same, If we have a longer distance, it's going to seem like a longer time. This one is a shorter distance, so it seems like a shorter time, okay? Because it is the speed of light, c, that is constant, okay? Now, there are equations for this, but they are beyond the scope of the AP curriculum, and you don't need to worry about them. I did do a quick little summary chart as well, summarizing the difference between special relativity and general relativity. Now, you don't really need to make much of a distinction between these. In general, though, special relativity has to do with objects that are moving at constant speeds, where general relativity has acceleration. And general relativity can explain space-time, and the special relativity we had before did not. Okay, so yeah. How does this connect to wave-particle duality? Okay, so energy and momentum, okay? You might have heard that question like, how can photons move sails if they don't have mass? How can they have momentum and impart that in a collision, okay? And that is really through that energy. So we know that the energy of a photon we can find from HF or HC over lambda. And then we also know that energy equals mc squared, okay? So actually, I'm going to use the HF one, okay? So if we're looking at this, these energies are the same, okay? It's energy. So it becomes HF equals mc squared. I was right. I was going to use the HC over lambda, okay? Because then in the frequency, okay, we can see the c squared cancel out with that, okay, and leave just one c. And then we have h over wavelength equals m times c. And hey, what did you know? That is a velocity. Mass times velocity equals momentum. So we get that momentum of a photon equals h over wavelength, where that is the de Broglie wavelength when we apply it to particles. Okay, cool. Okay, cool. This also has a little bit to do with the Heisenberg uncertainty principle, which is the more precisely that we know the location of a particle, the less precisely we know its momentum, and vice versa. Because in order to detect a particle, whether it's a photon or an electron or a proton, we have to interact with it, either by putting it through an electric field, photons, okay, by shining a light on it, photons, okay? We interact with it and we change its momentum. Not by a lot, okay, but by a little bit, which can become important at the scales of quantum physics, okay? Now, from all of that, everything you need to know about relativity and spacetime in the AP Physics 2 curriculum can be summed up in these two sentences. Time and distances are not constant. Okay, if two people are moving at different speeds, they might not agree on time or sizes of things or distances of things. Okay, but they will agree on the speed of light. Okay, that is the only constant. And if you are moving faster, closer to the speed of light, that will shrink distances and slow time. Okay, shrink distances and slow time. Okay, cool. That's it for our AP Physics 2 curriculum. You guys got this. Bye.